As the use of radioactive materials increases, the problems associated with the disposal of the wastes become ever more important. Of all known toxic materials, radioactive nuclides alone cannot be detoxified or rendered harmless by any known chemical or physical processing. Safe disposal of these materials requires that they be so segregated that any return to man is in such a low concentration as to be certainly harmless. All manner of possible return paths must be considered in choosing a processing and disposal method. Disposal by burial on land requires the utmost care to ensure that there is a negligible contact between the waste product and water sources, through which the isotopes might return to man either directly or through food chains. When intermediate products such as edible plants, animals, and fish are involved, the effects of biological concentrations of particular nuclides in these intermediates must be carefully appraised. At the National Institutes of Health, the Radiation Safety Office is the organization responsible for all radiation safety operations. These operations include the processing and disposal of radioactive wastes. Safety office functions center around the isotope laboratory, located apart from other laboratories and service buildings. The disposal methods to be shown are the result of over 10 years of development in cooperation with the United States Coast Guard. The deep sea was chosen as the most desirable ultimate depository. Burial at sea must be carried out so there will be no interference with either commercial or sport fishing. No significant concentrations of any isotope deposited must appear at the surface of the sea or on any beach. The waste disposal area, approximately 90 miles due east of Norfolk, is over 1,000 fathoms in depth. Radioactive waste processing and packaging is carried out in a restricted area near the isotope laboratory. This area is surrounded by a custodial fence to separate it from the activities and traffic of the institutes. The waste of low activity will be disposed of directly into the regular sewer system, with water flushing the sample down the drain at the disposal time. This other waste, which was found to contain somewhat greater activity, will be put into a special sewer system. This leads to a large underground retention tank, where the waste will be held for an appreciable length of time before being released to the municipal sewer system. Both of these wastes are short half-life, or else disposal by either of these means would not be allowable. Waste containing carbon-14 or tritium cannot be classified by the crude assay method previously shown. With these weak beta emitters, carefully prepared samples are counted in a liquid scintillator. The scintillating solution and the photomultiplier tubes picking up the tiny flashes of light are kept at a very low temperature in a deep freeze to reduce the effect of extraneous disturbances on the electric circuits. Carbon-14 and tritium wastes that are too concentrated for direct disposal will be kept for burial at sea. Each of these nuclides has a half-life that is too long for appreciable decay to occur during any practical storage period. Another source of active waste material comes from animal experiments. This animal has been injected with a long-lived radioactive material. Note that the experimenters are wearing rubber gloves to avoid contamination of hands. Blood samples are withdrawn, placed into counting planchets for drying and subsequent assay. Marking tape is used whenever radioactive material is involved. It is most important that all packages be so marked and an approximate value given of the amount of the isotope present and the isotope identified. Animal carcasses are stored at low temperature until ready for disposal by approved methods. Since licenses for radioactive materials are given by possession limits, it is necessary to keep a careful account of the isotopes that are thrown away. Each package must be marked with the amount of the isotope which it contains. Throughout all waste disposal operations and processing, accurate records are kept of radiation exposure of all personnel involved. Film badge monitoring devices are loaded and prepared for issue throughout the institutes. A most important part of the monitoring consists of keeping records. Most of these records will be needed perhaps 5 to 10 years after they have been entered. So neatness, accuracy, and legibility are most important items in the record keeping. Records must be kept of all radioactive waste materials that are disposed of by whatever means. This represents about 1/2 of a day's collection from the laboratories and clinical areas at the institutes. Delivery of radioactive materials to the Radiation Safety Office is made so easy that there will be little or no temptation to dispose of these materials by other methods. Otherwise, these radioactive materials might be found in the regular trash containers or dumped indiscriminately into the municipal sewer system. The polyethylene bags are the liners of the waste containers which are handed out to all users of active materials. Wastes are classified and records kept of each package, its location, and the method of final disposal. Here, materials of short half-life are being kept for decay and for later incineration. Materials which have too long a half-life to allow decay to take place will be put into children-sized concrete burial vaults for ultimate disposal at sea. Liquids, solids, and activities of many different levels are some of the diverse materials which are collected. Vaults are standard, commercially available containers of convenient size. They are made of steel-reinforced concrete and have lifting eyes cast into the bottom. Short lengths of steel cable are attached to these eyes for handling. The vaults are packed as carefully as possible to include a maximum amount of material. This cuts down the number of containers required and aids in obtaining the density required to ensure sinking in the ocean. Special waste products require special methods of handling. Here are the steps that lead to the ultimate disposal of some cobalt pellets. They have already been packaged in lead and welded into a steel pipe. Spacing rings encircle the cobalt container so that the pipe will be centered into the steel disposal drum. The drum will then be filled with concrete. Although there is some gamma ray activity at the surface of this steel container, the handling is done without intervening shields because of the relatively short time involved. Observe how the centering devices help as the pipe is lowered into the drum. Note the marking of the drum to indicate that it now contains radioactive materials, the amount and isotope being marked on the label. A wet concrete mortar is now poured around the steel container containing the cobalt pellets. The concrete in this particular case fills the drum readily without any tamping, and a solid mass will result without any agitation. The concrete can be mixed to any desired consistency. The steel pipe is suspended from the top of the drum to prevent it sinking through the soft mass before the concrete hardens. An immediate check is made of the surface gamma activity of the container. This is to make sure that it will comply with all of the interstate commerce regulations governing the shipment of radioactive materials over state highways. The markings on the drums are made in accordance with requirements of AEC licensing. They cover the amount and the isotope contained therein, also identifying marks so that if there is any future recovery, the origin of the drum can be identified. Waste materials are packed in the concrete burial vaults and mixed intimately with a thin concrete mortar. All of the polyethylene containers are broken to ensure an intimate mix with the concrete and also to obtain a maximum density to ensure sinking in the ocean. Vaults are shallow enough to permit good mixing of the contents with thin concrete. The safety office personnel working directly over the vaults wear respirators to prevent the inhalation of airborne radioactive materials. This is not considered necessary for the cement workers who have a casual contact and are not working directly over the vault during the active breaking of the polyethylene containers. The vaults are actively agitated during the entire filling operation to eliminate voids and obtain as intimate mixing as possible. Actual tests show that the finished containers remain intact under the hydrostatic pressures at depths of at least 6,000 feet. Vacuum pumps used on a radon plant are contaminated to an extent where decontamination would be more expensive than replacement. So they are disposed of along with other types of wastes. This is a sample of the wastes collected at an institution such as the National Institutes of Health. The vaults are finally sealed with a few inches of richer cement mix than is used in the body of the filling. These vaults shown here represent about 1 day's processing and contain approximately 6 months' waste supply from the institutes. Upon completion, they are checked for gross gamma activity with the gamma-sensitive meter. Each vault must be marked with identifying symbols to show the isotope contained therein, the approximate amount, the authorization permits under which shipment is made, and marks and dates for NIH identification purposes. The radioactive materials contained in these vaults are considered to be Class D poisons and therefore require the use of Interstate Commerce Commission labels, as well as direct identification as radioactive materials. The new concrete surfaces are painted to reduce moisture absorption while awaiting final disposition. The finished vaults are now checked to be sure there is no surface contamination. This is done by making a series of wipes across the surface of the finished concrete. As the vaults are made ready for loading into trucks for transportation to the port of embarkation, a final gamma check is made on each individual vault to be sure that it fulfills the requirements for transportation over public roads. Each truck is loaded so that very low activity vaults, or those containing only non-penetrating beta emitters, are placed next to the driver. This provides additional shielding between him and any vaults which show an appreciable gamma activity at the surface. This precaution is perhaps unnecessary, but is carried out simply because any radioactive exposure should be avoided whenever possible. Each convoy is accompanied by a trained monitor in a separate vehicle, carrying monitoring instruments capable of making measurements at any radioactive emergency which may arise during the shipment. A truck convoy leaving for the port of embarkation must comply with a variety of regulations. The convoy ends at the Coast Guard base in Norfolk, Virginia, where the waste containers are loaded onto the fantail of the Coast Guard cutter. This vessel is equipped with steel trays, which prevent contact of the waste container with the wooden deck, and in addition, raise the shipment to a level that will clear the rail of the ship during the dumping procedure. One of the larger trays, shown here, is equipped with sections of roller conveyors to facilitate the offloading of the concrete vaults at the designated dumping site. The steel platform is for handling the steel drums. Each set of concrete vaults is locked in position by a special locking device, which can be tripped at sea for the safe release of the containers. As in the case of loading the trucks, preference is given to those vaults showing some gamma activity at the surface by placing them outboard and away from the positions which will be occupied by the crew during the normal working of the vessel. It will be noted that here the crew members are handling the vaults without protective gloves because of the previous checks, which have shown the surfaces to be completely free of radioactive contamination. Aboard ship, steel drums are lashed down to prevent movement during the voyage out to the dumping ground. The hands and feet of the crew members are checked to be sure that no contamination has been received by any of them in loading the vaults and drums. These surveys are conducted with a Geiger counter, which will respond to carbon-14 and more energetic emitters, but which will not detect tritium. With the thorough mixing of the wastes, it is hard to imagine a contamination of tritium alone. And so an absence of activity is assumed to indicate an absence of tritium also. Tripping a dog releases 4 vaults, which go overside almost simultaneously, but without any damaging collisions. This is done at the dumping ground, prescribed in the waste disposal license, granted by the Atomic Energy Commission. Experiments conducted at depths of 1,000 fathoms or 6,000 feet suggest that about 15 to 20 minutes is required for containers to reach the bottom. All materials are disposed of at a depth of not less than 1,000 fathoms, which in the Norfolk area means approximately 80 to 90 miles due east to carry the ship beyond the continental shelf. Here, the fathometer reading for one particular trip indicates that disposal is made at a depth of 1,000 fathoms.